There are two problems. One we don't know until the end of next lecture. But here's problem number 4. It has a matrix A that has 2 minus 2, 4, 4, 4 minus 5, 7, minus 2 minus 2 minus 8, 1, 3, 6, and the right-hand side B, which is given by 3, 1, 10. And then the questions are, well, the first one is always on the final. Find the general solution AX equals B. Show me that you've learned how to solve AX equals B. Then comes a little bit of extra stuff that one can do now that I've written it. Is T 1 to 1? Explain. So we'll do 1 to 1 and all to both of those. Find the dimension and basis for the null space, the column space, and the row space. And then find the unit vector in R4 that's orthogonal to the null space of A. So having understood the fundamentals here is what the last one is. So let's just run through it. We have to solve. So pivots in the first row over here, then for the first column. Everything else is the identity matrix, 0, 0, 1. To get rid of that, minus 2 is plus 2 divided by 2 is 1. Minus 4 divided by 2 is minus 2. So that's going to put zeros in here. Copy the first row, 2, 4, minus 2, 1, 3. First row plus second row, the 0 we wanted, minus 5 plus 4 is minus 1. Minus 2 is minus 4. 3 plus 1 is 4. 3 plus 1 is 4. Last row, minus 2 times the first row, the 0 we wanted. 7 minus 8 is a minus 1. Minus 8 plus 4 is minus 4. 6 minus 2 is plus 4. 10 minus 6 is plus 4. See what's happening? So here's my pivot. Here's the next pivot. Pivot is now in the second row, therefore second column, and everything else is the identity matrix. So this number, to get rid of this one. Plus 1 divided by minus 1 is minus 1, and therefore, copy in the first row, 2, 4, minus 2, 1, right-hand side 3. Copy in the second row, 0, minus 1, minus 4, 4, 4. Third row minus the second, 0, 0, 0, 0, 0, 0. Pivot, pivot, row echelon form, consistent. So we have a solution. Let's find out our variables. So here we have a pivot, a basic variable x1, a basic variable x2. The remaining ones are free. So x3 is equal to alpha. X4 is equal to beta. There's only 2 of them. X4 is equal to beta. Let's write down the solutions therefore. We have X3 is equal to alpha. X4 is equal to beta. And then transcribe it. We see that X2 is equal to, divide out the pivot, so we get a minus sign on the right-hand side. Right-hand side 4, plus 4 times x3, minus 4 times x4. And so this is equal to minus 4. Minus 4 times x3 is equal to minus 4 alpha. And minus those ones is plus 4x4 plus 4 beta. And then the x1 variable, x1 is equal to 1 over the pivot, 1/2. Right-hand side is 3 minus 4x2 plus 2x3 minus x4. One reason I'm writing the x's here is because I want to make sure I read off the right x variable. So it is equal to this, and therefore 1/2 times 3 minus 4 times x2 minus 4 times minus 4 minus 4 alpha plus 4 beta plus 2 times x3 plus 2 alpha minus x4 minus beta. So this is equal to 1/2 times constant terms. Minus times minus is plus 16 plus 3, that's plus 19. Okay, plus 19. Then the alpha terms. Minus times minus is plus 16 alpha plus 2 is plus 18 alpha. And the beta terms, minus times plus is minus 16 beta minus 1, so minus 17 beta. Somebody went to town with those numbers. That's equal to 19 over 2 plus 18 over 2 is 9 alpha minus 17 over 2 beta. So when I write down the solution, therefore, I have 4 variables, x1, x2, x3, x4, equal to a constant vector plus an alpha term plus a beta term. And so let's see, x1 is 19 over 2 plus 9 alpha minus 17 over 2 beta. x2 is equal to minus 4 alpha plus 4 beta. x3 is equal to 0 plus 1 alpha plus 0 beta. And x4 is equal to 0 plus 0 alpha plus 1 beta. This here is a particular solution to the problem. Plug in any alpha, plug in any beta and add them up, and you get another particular solution, right? So however many you want. This over here, these are the homogeneous solutions, the solutions of Ax equals 0. So they are the null space. So we found all the spaces, all the solution. Now if you want to go for the spaces in terms of the column space, we have pivots over here. So this vector is a basis vector for a column space, and this vector, these two vectors together are basis for a column space. Basis for the row space, they are this one and that one, pivot vectors over here. And then basis for the null space, here and here. Now, before I go and write down the basis, how would I quickly check whether or not I did this right? That claims to be the solution, right? This vector here is supposed to be a solution. So if I multiply my matrix A by that vector, by 19 over 2, minus 4, 0, 0, I expect to find this vector. Similarly, the next two vectors should be, when I multiply into A, should give me 0. So 9 minus 4, 1, 0 should give me all zeros. And finally, minus 17 over 2, 4, 0, 1. When I multiply that in here, that should also give me 0, 0, 0. So I'd have to multiply that to check. I'm not going to bother given that there are halves in there. It's too messy to go near that. I'll claim either. Correct me if I'm wrong. So, a couple of things here now. First thing is all our spaces. And I'll just write the bases and dimensions and the rank. What's the rank of the matrix A? Richardson? The rank is the number of pivots. How many pivots? 2. Okay, so rank of A is 2, the number of pivots. I picked on you because you asked me, I want to make sure it sense. So rank of A is 2. The basis for the column space of A is the two vectors in the matrix A that have pivots in them, 2 minus 2, 4. So I could scale them, right? 1 minus, is it 1 minus 1, 2? Just scale out the factor of 2 from that basic vector, it's still a vector in the same direction. Right? It's still the same coordinate axis. This one over here, 4 minus 5, 7. And the dimension of the column space of A is equal to the rank of A, the number of pivots is equal to the number of vectors in here, is 2. The basis for the row space of A, these I picked from the rows over here. 2, 4 minus 2, 1. And 0 minus 1 minus 4, 4. The dimension of the row space of A is the rank of A. The number of pivots is the number of vectors we have here is 2. The basis for the null space of A is equal to, well, the homogeneous solution vectors, 9 minus 4, 1, 0, 9 minus 4, 1, 0, and minus 17 over 2, 4, 0, 1. The dimension of the null space of A is the number of columns minus the rank, so the number of free variables, is equal to, we've got 2 of them in here. And just for the fun of it, let's quickly think about the fundamental theorem and figure out the dimension of the null space of A transpose. So X belongs to something, Y belongs to another R. We are transforming Y equals A times X. For A times X to be possible, X has to have 1, 2, 3, 4 entries in it. So X sits in R. Y then sits in the number of rows, sits in R. This space here, the row space of A, the row space of A transpose is the column space of A, the null space of A, and the null space of A transpose. The rank of A was 2, so this has 2 vectors in it, dimension 2, dimension 2. Null space 4 minus 2. Null space indeed has 2 vectors. Null space of A transpose 3 minus 2. Oh, the null space of A has to have this single vector. So here, we found the spaces. Now let's go back and reread our problem. A. Let the linear transformation T from R4 to R3 be given by A times X. Okay. So from here to here, from this R4 to this R3, this is the transformation T in that state. Okay, so T takes me from R4 to R3, and it has that matrix representation A times a vector. And the question we're asking is this transformation 1 to 1? What does 1 to 1 mean? Why? What does 1 to 1 mean?
It's like a unique solution, so you can't have like any arbitrary like alpha or beta.
I can't have alphas and betas because what that means is 2 different starting points end up at the same end point. 1 to 1 means whatever end point I get, there's only one possible place to start from. So the explanation for part A is T is not 1 to 1. One way of saying that is the dimension of the null space of A is greater than 0. There's more than one place to start from, right? There's an infinite number of ways of starting points, all end up at the same endpoint. So, for example, I have, if I pick a starting point alpha equals 0, beta equals 0, so 19 over 2 minus 4, 0, 0. If I apply t to that vector, if I multiply that by a, it goes to 3, 1, 10. And if I pick, say, alpha equals 1, beta equals 0, then 19 over 2 minus 4, 0, 0, plus 9 minus 4, 1, 0. This vector here, by t, also goes to 3, 1, 10. Not 1 to 1. Okay. Is it onto?
No.
What does onto mean?
You have to have a bit-
No.
Onto means pivot in every row. But why? What does onto mean?
You can reach all the.
I can reach every possible right-hand side. I can't allow a contradiction. If I could get a contradiction out of it, it's not onto. That means I can't have a row of zeros. That means a pivot in every row. Do we have a pivot in every row? No.
No.
Not onto. It's not asked for, but if we did, we could also say t is not onto. There are right-hand sides we can't reach. There's a row without a pivot, and therefore what? If I were to start with a contradiction here, 0, 0, 1. Now I can unravel what I did to go back to a starting vector over here that leads to 0, 0, 1, that leads to a contradiction. I can't reach this guy. So not 1, 2, and not 1, 2. So let's read it. Find the general solution to ax equals b in the form x equals particular solution plus homogeneous solution. Okay, we did that. Is t 1 to 1? We wrote down an explanation. Dimensions and bases for null space, column space, and row space. We wrote all three. Extra credit. Find a unit vector in R4 orthogonal to the null space of A. Null space of A. Orthogonal is the row space of A. Oh, I want to find a unit vector in the row space of A. Okay? That's what the number 4 meant. So let's write that out. Part E. Find a unit vector orthogonal to the hyperspace, the null space of A. And so I.e.